Hello there, thank you for joining me again today. On the bench we have for review a Marconi IFR Aeroflex 2965A radio test set. This particular test set boasts a frequency range from 100 kHz to 1 GHz and is a fully featured radio test set. You may recall, if you haven't seen already, an earlier video that I did on the same looking test set that's called a IFR 2968 model, a higher model than this, which I did a review on. That radio test set is a Tetra radio test set. Now, one of the things about these test sets is they all started with this model as the base model. So it's like 4 models in the range. There was the 2965A, which is this one, the 2966A, the 2967, and then the 2968. But they're all based on this chassis, this graphical user interface style, the same hardware, but just different options fitted on the systems, which we'll go into a bit later in the video. But those of you who may recall the Tetra radio test set, which is this one here, although it's a higher model, it was made earlier than this particular test set, because this has got the IFR branding on it, whereas the 2968 that I have has got Marconi branding on it. And obviously Marconi came before IFR, and then Aeroflex came after IFR, and then it's obviously been taken over again since. So this is a newer test set than the IFR, than the Marconi 2968, but the 2968, this one has the same features as this, except with it being a higher model it has more options on it, which you'll see in the other video if you look at that on the Tetra radio test set, because that other test set does Tetra measurements on digital radio standards. This 2965A was sort of a continuation on from the Marconi theme. As you may recall earlier, on some of the other videos that I've done, the very start of it all really with the 2955 radio test set, it was Marconi's combined method of instrument, whereas prior to the 2955 they didn't manufacture a radio test set as such that had all separate instruments combined in one. What Marconi did is they manufactured separate instruments up to then. They were manufacturing signal generators, mod meters, frequency counters, many of which I've demonstrated on this video. They still continued that theme, but they didn't have a fully integrated radio comms test set until sort of in the mid 1970s, when they produced the Marconi 2955 radio test set. Again, please check out my channel. There's other videos on those test sets, indeed demos of the 2955, 2955A, 2955B and 2955R with a sensitive receiver option. And those test sets were the very first radio test sets that Marconi Instruments produced, that were all in one instruments like this. And they evolved through the years, through the 70s and 80s and into the early 1990s, when they produced a Marconi 2955B radio test set, which I've done a repair video on very recently, and they went to a white frontage radio test set, and that then had more appealability with the look of it, a nice white clean appearance, rubber keys instead of plastic buttons, and we went from there then to a 2945 radio test set, which was more of a smaller unit, a bit narrower from top to bottom, and it had rubber keys again, but it had an LCD screen, and it was quite a wide screen. The test set was sort of quite elongated from left to right, but it had a narrow wide LCD screen, and they were around for some time. They aimed at the avionics market, and they also aimed at radio telecoms maintainer markets, etc., and testing. They weren't around for too long, the 2945s. I think they had one or two issues with the LCD failures happening on them, and there were a number of them that I had over the years. But then came along these test sets to replace the 2945, the 2965, 66 and 67 and 68 series radio test sets. And one of the nice things about this is that they went back to a CRT on this model instead of an LCD display, for more reliability, I think, due to the numerous problems they were having with the IFR 2945. And then they also created this series of test set that had basically the same hardware base, but you could, if you wished, add system options. And indeed they designed it in such a way where they were just more or less plug-in options, as opposed to having to redesign or fit certain types of PCBs in to accept options. That was all designed out so that basically you could just software enable an option under systems, and then as long as the option board was installed, then it would emulate that system. So that's where they went away from this, what they used to have in the earlier models, where you physically had to introduce hardware modules, and some in order to make that test set do that, you had to have a prerequisite in the form of a PCB already in the machine that could accept that option. And there was some RF cabling that needed to be done, and there was other mechanical interventions that needed to take place in order to allow that option to be installed on the earlier test sets. So with that, it was sort of designed out that they wanted something that was more flexible and that you could you know, use without too much aggro in adding options or doing what you needed to do to the test set to make it what you wanted, and it was quite flexible. Also on this particular model of test set as well, we still kept the memory card, which Marconi adopted on quite a lot of their test sets from the Marconi sort of 2945 radio test set is where that started from. Now this particular test set has quite a lot of really good options on it as well, generally as standard, even before you start adding all the system options, in the fact that it's got a 150 watt rated RF port here. We've also got a spectrum analyzer, a tracking generator, audio analyzer. We've got an RF test option as well for measuring loss, etc., which I'll go into a bit later, and another RF testing out test capability. We've got the systems option, obviously, so we can go into different systems. It's more or less the same type of architecture as the other predecessors to this, but it was just that the way they've gone about this is slightly different with the menu options on the top, bottom and right. So you basically got as graphical examples of different functions appear on the left, right, bottom of the screen. You can select them using this particular functionality as each screen appears by these screen edge cursor buttons. We've more or less kept everything else the same, except we've also got a nice addition of a voltmeter and a current meter, which again aids in fault diagnosis, maintenance, testing, etc. We have an off-air receiver standard on this, and that's why we've got the Squelch control. And then also there's an SSB option on this particular test set. Most of them have it, so you can use it with SSB radios as well, which is quite handy. So what we'll do, we'll do a few measurements. I've got a radio transceiver on the top. We'll show you the full capability of receive, transmit, the radio options that are on there. But just looking at the keyboard in general at the front, we've obviously got the slot here for the memory card to plug in. We've got the usual data entry keys, the megahertz, kilohertz, hertz, dB, microvolt, dBm, millivolts, microvolts, volts. Here we've got what is the function. So we've got frequency, increment, level, copy, channel, store. We've got deviation, depth, recall. We've got the usual buttons in green here, which they kept the same key colours on most of the test sets in the Marconi range. So we've got RF Gen, TX, RX, mod frequency, mod gen, and then we've got the main modes down here, obviously TX test, RX test, Duplexer, tone systems, and then we've got RF test and AF test, and then a help setup function. As I say, all these buttons here are all across around the outside of the screen that represent the options that are displayed in the screen. And then we've got the voltmeter, intensity, scope position, and we've also got the volume for the speaker, integral speaker and Squelch controls. We've got an external mod input as well for different modulation standards to be fed in, an AF output for generating audio signals, and then an AF input rather, and then an AF gen output. We've got a low and a high power port here. This particular port can be configured in different ways depending on what you're doing, so it can be used as an in and out. You can send signals in and out on either port, and you can adjust it, flip it round under Duplexer test for doing all sorts of different configurations. You can have everything on that low power port, or everything on the high power, or a combination of both. We've got the vernier variable control, and then we've got AC/DC coupling as well that we can have on the mod or the AF gens as well. Now, as well as that, I think it boasts a 20 memory. If I press the recall button onto the memories, recall, I think we've got next page, total of 20 memories. So you can store memories as well within the instrument. It can store up to 20 memories, I believe, as we can see there, maximum, because when I press the next page again it goes back to zeros. So you can, if you wish, if you wanted to store that particular screen, you can just do store 01 and then press that says store there, and then you can call it what you like. So you can then, if you wish, I think you can use the characters that are here. You know, you can select, go through different characters, and then when you're done, then just press enter key, and then you should be okay. Now, looking at this, I think the enter key is actually that dash. Oh no, let's have a look. It's that key there. That's the key, the enter key. It says it there, look, just above dBm. So now when I do, for example, if I'm in Duplexer test already, and then I do recall 01 and then press enter, then it'll go back to that screen that we've already saved prior. So yeah, you can save up to 20 memories on it locally. There's a card that plugs in there that you can store all sorts of different tests on, and that as well. So we'll connect up the radio transceiver now as well, and we'll do some RF testing. One of the other things as well is that it doesn't have a power switch at the front, and I don't know why they did that. IFR forgot to put the power switch on the front. Even just a toggle switch here would have been brilliant, because when you've got this instrument stacked up with a load of other gear, or inset into a bench where you know you're doing quite a lot of maintenance, and you've got a bench that's set back away from you, or a shelf above slightly higher than the bench, it's a bit weird, but you've got to hand round the back. There's a power switch right at the back. You've got to feel round the back and flick this toggle switch in order to power it on, and it's a bit of a weird place to put it, but that's just the design that they've gone with. Whereas the other test instruments that I've got mainly all have switches at the front. Rode and Schwartz tend to have gone back to the switches at the back for some reason, rather than having them at the front. But it just seems that that's the way of the world with this particular test set. Right, we'll do some RF testing. Okay, so we're ready to do a transmitter test now. We've got the radio transceiver connected to the high power port on the instrument. At the moment we've just got the test set to Autotune, so we'll show you that feature. One of the important things to notice on this radio test set as well is that it has a separate IF bandwidth, which you can alter by pressing the IF bandwidth key here. It defaults to 280 kHz, but the beauty about this, which you don't get on the other test sets really, is that the fact that you can narrow down the RF carrier. So if you're doing precise noise measurements of an RF carrier without the modulation, for example, in more of a research laboratory type scenario or design role, where you're designing an RF circuit, you can actually reduce that right down, the IF bandwidth, so that you're excluding some of the noise which would be on the sidebands of the signal, and in doing that then you can make more accurate measurements, particularly when it comes to noise levels of amplifiers and things, not just radio transceivers, but when we're actually measuring radio frequency components, so not just radio systems. So that's an interesting feature which you don't get on a lot of test sets actually. We've also got, for RF power measurement, we've got broadband, but we've also got in-band power as well, so we can actually select broadband or narrowband power if we want to look at not to include harmonic RF energy, or where we have radio systems that have multiple carriers, so that's quite useful. But at the moment we've got TX-Tune set to on, so basically whatever frequency the test set picks up, it'll lock to that and tell us what the frequency is. Alternatively, we can select that to off, and you can enter a frequency in, and then it'll tell you what the offset is. So when you're transmitting into the test set, it will tell you what error the radio's got. So if the radio's off tune, needs its reference oscillator VCO adjusting, it'll tell you that here, because obviously the error will be too far off, and that'll be denoted by the specification in the equipment service manual that accompanies this radio transceiver that you're testing. So what we'll do, we'll just transmit first. What I've done first of all, we'll just have it on Autotune with the ctcss filter. We've got a filter here, an audio filter set to 300 Hz low pass. So basically ctcss lies between 67 to 250.3 Hz. So any frequency in that which is below the speech band will be picked out, and it'll ignore my voice on the microphone, so that it'll also display the frequency here where it says mod frequency of what the ctcss tone is. So I'm just transmitting now, and then it's going to tune to the frequency, which it's done there. We're reading the RF power, we've got a ctcss waveform, and then we'll be able to display the frequency. Now it's telling us there that it's 350 Hz FM deviation. If I increase the amplitude so that we can see more of that, then we'll be able to read the frequency of 77 Hz. So that's what the frequency that tone is. Now I can hold the microphone up to mouth, which I'm doing now, and the speech isn't being seen on the bar graph. But when I select band pass, and now 1 2 3 4 5 1 2 1 2 radio test, so now we're starting to see the frequency and modulation of my voice. 1 2 3 4 5. So we can so that's 2 kHz per division, that's 4 kHz per division, that's 8 kHz. 1 2 3 4 5 1 2 3 4 5 1 2 1 2. So you can measure the deviation as well. It'll tell you there, FM deviation peak 5 1 2 3 4 5. So one of the measurements that you can do with that is you can actually connect into the microphone input on the radio the AF gen out, and the service manual might say adjust whatever setting in the radio to give 4 kHz deviation with 100 millivolts at 1 kHz audio drive going into the mic input on the radio. So that's a particular thing that you can look at. Obviously we've got the RF power measurement that you saw, we've just seen that on the oscilloscope. We can also do that on the bar graph as well. So if we turn bar charts on, again, if I transmit, we'll have deviation and power measured. 1 2 3 4 5 5 4 3 2 1 1 2 3 4 5. So it gives us RF power and deviation. So that's a quick rundown of what you can do on the transmitter side. We've also got a spectrum analyzer as well. When we have a look down here, we've got a mod analyzer too, and a spectrum analyzer. We'll just look at the mod analyzer, and then when I transmit in 1 2 3 4 5 5 1 2 3 4 5 5 4 3 2 1 1 2 1 2 1 2. So there you can analyze the modulation bandwidth. So that's pretty useful for seeing if there's any out of band frequencies which might be allowed through the pre-emphasis and de-emphasis circuits of the microphone amplifier circuits, because we don't want it producing frequencies, audio frequencies, outside of the normal 300 Hz to 3.4 kHz audio spectrum. So that's quite useful for that measurement. In addition to that, we've got the spectrum analyzer. So obviously at the moment it's set to Autotune. If I transmit, then it'll find the best range for the spectrum analyzer as well as the frequency and lock onto it. We can increase that if we want as well, expand on it, so then it'll give us more of a picture of what we've got there. We can increase the input levels as well accordingly, the span, and it's reading my whatever it's picking up on the mic plus the ctcss on there. We've got a resolution bandwidth up and down as well, so we can increase the resolution bandwidth or decrease it accordingly. And then of course we've got auto resolution bandwidth. We have max hold as well if we want to measure levels, and dB per octave we can set that as well, 10 dB or 2 dB, whatever we want. So we can do quite a bit with that. So back to TX test a moment. What we can do as well, we can measure the frequency accuracy of a transmitter to see how aligned to frequency that particular radio is. And how we do that is we knock TX tune to off, and then we enter a frequency in. So we select TX frequency. In this case, I'm not sure what the frequency was actually. Was it 1875? 145.1875 megahertz. And if I've chosen the right frequency now, when I transmit, it should tell us the offset. So it's telling us there it's 220 Hz off frequency, or 60 Hz, or 180, it's varying a little bit. If that was way off, like a kilohertz or whatever, off 900 Hz upwards, then you'd be tempted to readjust that so that it was on frequency. But obviously it's showing more or less bang on frequency there, so we're not concerned about adjusting the radio. But again, the specification for the offset would be in the service manual for the radio. But certainly if it's wandering off more than 500 to 900 Hz off frequency, 900 would be a bit of a warning bell for me. But if it's any higher than 500 Hz, I'd be tempted to adjust that down to 0, or as near damn it to 0 as you can get it. Obviously we've got the power still being measured. We're in band on the audio spectrum. 1 2 3 4 5 1 2 1 2 1 2. So that's all there. So we'll go on to the RX measurement now. So just to recap on the transmit side, when we're doing an adjustment or spec checking of a radio, we're looking for quite a few things really. First of all, we're looking for the frequency accuracy of the transmitter, which is why we have auto tune to off and we manually input the frequency that it should be working on. Secondly, if it is off frequency by a long way, then the radio needs adjustment. We also look for the transmit power. Is it doing the correct power, RF power? Is it too low? Is it too high? Does it need adjusting? Again, software or manual adjustments within the radio might be necessary. We need to look at as well the TX deviation, and that's very important, is the frequency modulation, deviation, is the fact that we don't want the deviation to be too excessive, because if it's too excessive it can bleed into adjacent channels, particularly if you're working at 6.25 kHz or 12.5 kHz divisional channel spacing, that if the FM deviation is too wide it can go off into the neighbouring channels and cause interference to other radio users neighbouring your frequency. So that's very important that we get that peak deviation. It's not the mean or average deviation, but the peak deviation within those limits. And Marconi have always been quite good at making test instruments that have got the oscilloscope, where you've got little dotted lines, and if I zoom in you can see there's these little dotted lines here, just there, and that's basically telling us that that's 8 kHz deviation between those two dotted lines. And so if I then adjust that, for example, down to 4 kHz, that's plus or minus 4 kHz in that dotted line area. And again, if I reduce that to 2 kHz, that's 2 kHz in those dotted line areas. So it gives you a really good capability to measure the total system deviation that's there, which is all the mod including. And it could be Selcall tone, ctcss speech, it could be other encryption type audio, it could be DTMF tones for telephone patching. All sorts of different tone signaling systems need to be at the correct modulation level. Normally, particularly in radio systems these days, analog radio systems, the signaling tones are normally 60% of the total system deviation. ctcss is normally set anywhere between 350 to 500 Hz on 12.5 kHz space channeled radios, about 600 Hz on 4.5 kHz deviation radios. It's normally about 60% mod for signaling systems such as Selcall and things like that. So you get a bit of a feel for radio testing as the years go on and you do different radio measurements. Again, a lot of the regulatory bodies in your countries will tell you what kind of modulation schemes or standards, what the acceptable deviation levels are, what frequencies, channel spacing. So depending on the country that you're in, what radio you're setting up and for what particular use will denote on what system deviation level, tone deviation, RF power, that kind of thing is all regulatory enforced by your radio regulators in your country. So for example, in the UK where I am, it's Ofcom. In the United States it's the FCC. In Europe I think it's the ETSI, European Telecommunications Standards Institute, and their representative bodies in different countries. So you get all these different regulatory authorities all over the world that as part of the radio license will tell you what the transmit parameters should be in regards to the modulation schemes, the power, and what you should be shoving out. Obviously radio transceivers can be aligned to work with different antennas, so if you're working with a collinear antenna that's got 3, 6, 12 dB gain for example, then your licensed power might be 25 watts ERP, effective radiated power, but that doesn't mean the transceiver is adjusted to 25 watts, because obviously that's what should be leaving the antenna, and if an aerial's got gain then you need to reduce the transmitter down so that the RF power is at the correct level before it gets to the aerial to then be boosted further. So that's the subject for another video probably we'll do later on. So that's the transmit side over with. We'll go over to the receive measurement now and show you that. Okay, so we're ready to do the receiver measurement now. I've got the radio transceiver still connected in the same format as we had before for the transmit test. I've gone to duplex screen. One of the little features that I want to show you on here is when I transmit, we should be able to get the frequency up there, which is 434.825 megahertz roughly, which is what we're transmitting on. Now in order to work the receive frequency out, because we're on a repeater frequency there, I need to then find that frequency on the receiver side. So if I wanted to, without trying to work it out in my head or go through band plans, you can do this with obviously radio systems. In most radio spectrums have a predetermined split which is unique country to country. In the UK they use various splits on different frequency bands between transmit and receive, particularly when we're using talk-through base stations, repeaters. On UHF, at least 4 that I know of, that it could be, but this is an amateur radio transceiver, and I just happen to know that the frequency offset between transmit and receive on repeater channels is 1.6 megahertz. So I could go to receive test, I could do for example RF frequency, and then I could put in 434.825 megahertz, which is the transmit frequency. I could then, say if I didn't want to work it out in my head or mathematically or a calculator, I could press the increment button on that and then set the frequency increment to 1.6 megahertz. So then we've got an increment there. Now if I press the frequency down button here, then that will then set up the receive frequency. Obviously it's just burst into life. Now what we've got, because we're going to be doing receiver sensitivity measurements, and we're also going to be doing what's called SINAD, signal to noise and distortion, and signal to noise measurements. So in order to perform those measurements, what we need is a lead that connects from the radio test set or from the radio on the back. There's a 3.5mm jack plug for the speaker output or the earphone output that comes back to the AF input onto the radio test set. So if we remove that, we don't get any audio at all. Right, so basically at the moment we're generating a receiver frequency. If I just zoom in on the screen a little bit more, so we've got the receiver frequency of 433.225, and that's the RF gen level in dBm. So if I do RF gen level, now I can adjust that level to what it says in the service manual, which would be 0.2 microvolts, for example. It could quote that, or neg 122 dBm for 12 dB SINAD or better. So if the receiver's deaf, or it needs tuning, or it's off tune, that will show up in that spec test, because if it doesn't meet that specification at that level, then the receiver's failed its specification tests, and we'd need to then do some adjustments. So what we're going to do now, we're going to measure the sensitivity. Now we'll measure it in dBm first and then microvolts. So I can start to crank that down. I'll set the scope on so we can see the waveform. Just adjust the level. So we're generating a frequency of radio frequency signal, which is a carrier wave, and then we're basically frequency modulating that with a 1 kilohertz tone at a deviation of 2.5 kilohertz deviation. And so if we over mod that, then it will distort in the receiver. If we under mod it, then we'll not measure the signal properly. So it's 2.5 kilohertz deviation in this case. So that's the waveform that we're getting out the speaker output of the radio. It's a 1 kilohertz tone, and that's the mod frequency it's receiving there. And now we can adjust the receiver. Now as I just adjust that, as I get the receiver to be noisy, it reaches a point where we lose the signal altogether, and then it comes back when we wind the signal up again. So we get that noise level out there, as you can hear. Just a very small, you know, you can have a signal as high as you want, you know, you can keep going up as high as you want. It never gets any worse, you see, until it gets really low down, and then suddenly we start to lose it, just in that few dBs difference there. We start to lose it. So this is where signal to noise and distortion comes in, the measurement. That's normally the measurement that's been adopted across the industry standard, basically, in radio testing around the world, is signal to noise and distortion, or signal to noise. Basically what SINAD means is that you're measuring the signal which is obviously the 1 kHz tone that's been recovered from the radio, the noise component, which is a crackle and hiss, and the distortion, so how distorted that 1 kHz tone is at that particular noise level. And so SINAD is a sort of rule of thumb specification that most radio manufacturers use in quoting in the receiver specification within the service manual, that would tell the radio operator or the radio engineer whether or not the radio is performing to the correct sensitivity and selectivity at the given radio frequency we're using. Now, in order for a radio receiver to be optimally tuned, we want the most sensitivity we can get for the best SINAD. So the better the SINAD at the lowest RF level, the more sensitive the receiver will be. Now, if the receiver is quoted to have 12 dB SINAD at neg 100 and say 20 dBm, if we find that at neg 80 dBm it's just meeting 12 dB SINAD, then that means that the receiver's got a fault, because neg 80 dBm is a very high RF level. It's way above neg 122 and neg 123. So in amplitude level the signal's a lot higher at neg 80 than it is at neg 123. And so if we were getting the desired spec that we needed from what is quoted in the service manual at neg 80 dBm, and the service manual said it should be that spec in SINAD at 12 dB at neg 122, neg 123, and we're getting that particular SINAD level at neg 80, that means the receiver's stuffed and we need to do something about it. Either a repair, component repair, a physical retune, software retune, a physical hardware retune, whatever's necessary. We need to do fault finding, we need to find out what's causing that. So we can do lots of different measurements. Sometimes the receiver's frequency can be off. So if the frequency of the receiver's local oscillator's wandered off too far, it can make the receiver insensitive at that frequency. And we can find that by just going to frequency and then adjusting the frequency up and down to see whether the receiver comes to life or not. That's if the reference oscillator in the radio's drifted off. So in other words, it's receiving another frequency close by in perfect spec, but not at the frequency we want it to be at. However, if it's not the reference oscillator, it could be the front end filters on the radio that have got a fault, or they need retuning, because the common problems that we all get with radios, particularly the older radios, if you've moved them a long way in frequency when you've reprogrammed them, a lot of the time you need to retune the receiver section because the frequency shift's been so large. And radios again come in predetermined bandwidths. In this day and age of like this particular radio, it's a software defined type radio. All the receiver front ends tuned in using software over a wide frequency range, but some of the older radios you need to whip the lid off and give them a tune up inside, because they're not made to move major frequency widths, if you like, 20 megahertz, 10 megs, and that's again quoted in the manual, the degradation of receiver spec over a given frequency bandwidth. So for example, this radio might want to tune from 400 to 470 megahertz without needing any manual intervention, whereas other radios can only tune 10 megahertz either side of the frequency that they're originally aligned on. So, you know, if you've got a radio on 440 megahertz and you decide to tune it to 460, it might be that receiver's really poor at 460 but great at 440, and that's because you need to go into the radio or software tune it or manually tune it, the front end, and we'll do that in another video as well. But for this test we've coupled the audio output of the receiver. That's the only way you can make SINAD measurements. Doesn't matter how you do it, you can go into an earphone jack, a micro speaker connection. Sometimes audio comes out of the mic socket at the front to a speaker mic. There's all sorts of different ways of coupling audio out. So we'll couple that back in. Now if I adjust the RF general level, and now what we need to do is introduce SINAD, which is this measurement here. So if I select SINAD to be on, that'll give us another measurement, and there we have it. So if I turn the volume down so it's not too loud, so it's reading 25 dB SINAD currently at neg 116.1 dBm. Now if I adjust that level, so we start to get to its 12 dB point, it doesn't take long to get there, does it? I mean, we're at 14, 13, call it 12 dB, just manually, very small, there we are, it's round about there, let's say neg 122, 11 dB, 12 dB Cyanide. Now in microvolt terms, if I press the microvolt button, which is down here somewhere, that one, that's 0.166 microvolts, you see. Some people work in microvolts, some people work in dBm, I work in both, but that's quite sensitive for obviously 12 dB Cyanide. So for example, in the manual for that radio it might say it's got to be better than 12 dB Cyanide at 0.2 microvolt. So if we're at 0.2 microvolts, if we increase that to 0.2, the spec might mean that it may say in the manual that is that level there, it's got to be better than 12. Well, it is, it's 19 dBs. So in this particular context, this receiver is very good, you know, it actually exceeds specification, but some receivers may not and they might need adjustment. So you know, it might be that you get a very low Cyanide reading at quite a high signal level, and then obviously we go up to fully quieted mode. Now there's a couple of reasons why we do this test, signal to noise and distortion, because a lot of receivers, the older receivers, they have a discriminator coil on the motherboard on the receiver section, and as part of the FM Foster Seal discriminators that they use, the discriminator has a peak at a particular IF frequency and then it falls off again, and so sometimes if the discriminator coil is not adjusted properly, you get distortion in the waveform. So even when the signal level's wound quite high up, so that it's fully quieted is the radio, so there's no noise on the carrier because the signal strength coming in is quite high and we're just recovering the 1 kHz tone that we're sending out to the receiver. Sometimes a distortion still occurs at that 1 kHz tone when there shouldn't be. It should be a perfect sinusoidal waveform and it shouldn't be distorted to any great degree, and so therefore basically that can come down to an adjustment in the receiver on what's called the discriminator coil. And so we'd peak that discriminator coil to get the most AC waveform at the minimist distortion. So we need to adjust that for minimal distortion as well as the higher level of 1 kHz tone that we can achieve. And again, I'll go into that on another video as well when we tune up some receivers, but that's what you're looking for. You're looking for minimal signal, you're looking for best signal to noise and distortion. Now we can put distortion on as well, that's another thing we can add. So it's only 2.9%. so again, the service manual might say that at a particular RF level, at this particular mod level, you've to achieve better than 2 dB's deviation, distortion. So if a distortion's higher than 2 dB's, then it means that you need to go into the radio and do an adjustment, and that's basically what that test means. There'll be other audio measurements as well where it'll say where you adjust the volume pot to midway. It'll say, for example, that you must achieve a certain amplitude of AF output as well into 8 ohms. So you'd introduce an 8 ohm resistor in parallel with the audio output from the loudspeaker, and so it will, the radio AF stages will be under load, the AF amplifier, and then you will then adjust the radio to give that waveform of audio output as well. We've also, under AF test as well, got audio input output test, that we can use that as well in synergy with some of the receiver side of things, so we can measure distortion, AF level in particular, and single out the audio component without looking at the RF side. We can then put on different filters as well. So if you're dealing with different signaling standards, for example, where you've adjusted the speech side of the radio, that you might then want to look at, say for example filtering out certain audio frequencies or audio signals that are also present on say a talk-through base station. Some of the line controllers have a high frequency control tone which controls the base station remotely, and sometimes that can break through into the receiver, and so therefore you might wish to notch that out, and some receivers allow that. You can either add hardware filters in there or software filters on the more modern radios to filter out any unwanted audio frequencies which may make it through onto the speech carrier breakthrough. So there's that side to it as well that you can do, but under receive test, that's what we're looking for. And we're also at that point as well looking to set the squelch levels, because indeed you can set the radio squelch up, so you can reduce the level in microvolts in this case right the way down, and we can set the squelch point, because if the receiver's too sensitive, then the squelch can lift, because sometimes the noise floor, depending on the solar system, the sun that produces radio noise, if you've got a receiver that's really sensitive that picks up a signal at 0.1 microvolt, when you connect it to an antenna, an external antenna, the noise in the atmosphere can then lift a squelch on the receiver, and so therefore the service manual might recommend setting the squelch at 0.3 microvolt. So the signal's got to be quite good in order for the squelch to open, so you get rid of a lot of interference possibly. If you're using the radio in a vehicle, for example, sometimes vehicle ignition systems can create noise in the RF spectrum which can lift the mute on the radio, the squelch, without a radio signal being present that you wish to listen to, and it can then just be noise, white noise you're receiving through the speaker. That can get annoying. In addition to that, there's other noise sources as well, local interference from other pieces of equipment that are nearby, such as power supplies, monitors, TVs, videos, all sorts of different types of equipment all produce electrical noise in the RF spectrum. And if a receiver sensitivity is very, very low, very, very good receiver sensitivity, it can pick up signals at a very low level, then naturally it can lift a receiver. So some radios have a tight squelch on them, so that the signal's got to be more or less at sort of this level. There's very little noise, more or less about there, before the squelch will lift. So it might set the squelch at 0.2 microvolt instead of 0.16, because at that level obviously it's squelched out there, but at that level it's very noisy. If you want me to understand, you sort of wouldn't be able to understand what was said at that level anyway, really. But again, some people adjust it for better sensitivity. So that's a little rundown of the receiver side of it. Obviously, if we wanted to test ctcss as well, and subaudible tone signaling standards or tones, which we'll look at a bit later regarding the tone systems, then you might want to set the squelch higher, because if you're sending a sequential tone out, Selcall, to a radio, and the receiver is the received signal's very noisy, it's difficult for the decoders in the radio to pull out those tones and decode them properly. So quite often, to prevent errors and tones that don't quite make it through because the signal noise level's too high, they normally set the squelch level quite high, so that the receiver's got to receive a good signal first before it can decode what you're also receiving in regards to tone systems or ctcss, etc. So it makes this radio system more reliable that way, and they're not just tuning everything for maximum sensitivity so it hears everything in the planet, but it can pull out what you want and therefore receive as a proper radio system, as opposed to just doing a load of crackles and noise, and particularly if you're on the extremities of the radio coverage, etc. So we'll move on to Dualplex testing now, and then the rest of the measurements. Right, one of the last tests as well that we can do, because we're obviously looking at distortion, signal to noise, and distortion. There's another test called signal to noise, and that's where we're measuring the difference between the signal, which is a 1 kHz tone, and the noise, which is that when the tone isn't there, the noise, if there's any crackle or pop or distortion, will be displayed. So that's what it's doing now, and then it displays that there, signal to noise level. So that's another spec, and then we can reduce the RF gen level. So that displays that, you see, signal to noise. So that's gives us a little rundown there of what we are looking at regards to the different things, the 3 different measurements there. We've had the signal to noise and distortion, SINAD. We've had distortion, and then signal to noise. So they're sort of the 3 AF measurements that we can perform in the receiver testing. Again, service information that comes with the radio transceiver would tell you what signal to noise, SINAD or distortion levels will be prevalent for that spec, that particular frequency banding and radio equipment. It would denote that in the specification for that radio, what that should be at what level. So that just demonstrates those 3 different levels. Obviously with receivers, they vary throughout different product ranges, manufacturers, frequency bands, the sensitivities are all different. Most radios, you know, in UHF spectrum can achieve about 0.2, 0.3 microvolts, some a little bit deafer than others. VHF, they tend to be variable as well, and HF, sensitivity isn't too much of a bigger issue at HF frequencies. Because of the way that HF radio works anyway, particularly with the different modes, which I'll go into later with the SSB testing and what have you. But the other thing as well is that we're looking at frequency modulation, but of course we can generate AM and phase modulation on this. So if we wanted to generate an AM signal, we would then set up the mod gen to, for example here, mod gen level. So we'll select mod gen level, and then we would set that up as a percentage if we were going to put in AM. Now on the older radio test sets, they had AM, FM and phase mod buttons here on the 2955s. On this test set, it's intelligent enough to know whether you're switching between AM and FM, because you're just entering the percentage if it's AM. So for example, I can put in, say, 60%, and that's the percent key there, mod, and then now we're generating an AM amplitude modulated signal. Now obviously this is an FM receiver, so I can't show the AC waveform there at the moment, but that just shows you the difference between setting up between AM and FM, is that rather than having a separate function key here for AM and FM, you just type in the percentage mod and it automatically knows it's an AM signal then that it needs to set up, and then if it's 1.5 kHz or 2.5 kHz deviation or whatever, then it knows it's an FM, and so therefore, you know, that's how you know the difference between setting up AM and FM on this radio test set. So just to show you the air measurement properly, we've inputted that 60% modulation at 1 kHz deviation at 1 kHz tone at 60% amplitude modulation depth. Obviously that radio can't receive it because it's an FM only, but the Hewlett-Packard radio test set that we've got over here can receive it. And as we can see there, we're generating 60% modulation at 1 kHz tone frequency. We selected there the AF input on the AF analyzer in to AMD mod, so we've got that set up. So that just shows the AM carrier, and if I go to spectrum analyzer on here, this screen's a little bit more difficult to see than some of the others. Let's just get rid of that. And there we've got the AM signal. So if I adjust the reference level, so that's the amplitude modulation that's coming out the test set. And obviously if I turn that mod off, then we've just got the carrier without the mod. So that's just a little rundown of the AM measurements for receiver signal being generated on the output of the N-type going off to the radio test set. And on that we did manage to select AMD mod on that particular instrument, just to demonstrate that. Okay, so we'll have a look at Dualplex testing now. So we'll hit the Dualplex button. Still got the receiver frequency set up and the AF level. We're still getting that AF level there, and then we've obviously still got the options that are available in the receiver side of things. We've got the RX filter, for example, distortion, Cyanide. Again, we can flick between them. So there's RX Cyanide, so you can perform that measurement in Dualplex as well. It'll give you the level, the Cyanide reading, and the filter. You can select the different RX filters as well. 5 kHz low pass filter, 300 Hz low pass, speech band 300 Hz to 3.4 kHz, CCIT I think it is, it's called. No filters, 20 kHz low pass, 5 kHz low pass, and then obviously back to speech again. So that's where we can get the receiver sensitivity. You can do all the measurements there still, RF gen level, frequency, Cyanide level, AF level, it's all here. Then the transmitter side on the right side of the screen, you can input your own frequency in, or you can let it auto tune under the TX frequency, or do what you like. There's obviously a speech band filter there as well, which you can select with these filters. TX tune on and off, obviously, as we just discussed. RF gen, AF gen on and off. So again, where we're looking at external AF gen output into a repeater to then check the talk through audio levels between transmit and receive. So we can generate audio signal into the transmitter section of the repeater to check the deviation there, as well as the talk through levels between the receiver and transmitter if it's a talk through base station. Because obviously if we're putting 2.5 kHz into a radio repeater on a Dualplex that can transmit and receive at the same time, the receiver would receive that frequency at that level. We want to make sure that the transmitter transmits out at the same level, so that the talk through levels, what's called talk through, is correct. Because obviously in Dualplex that implies that we can transmit and receive at the same time, which is what a radio repeater would do. It's listening for a receiver to be given a signal in the repeater from another radio, be it handheld or a mobile. The receiver in the repeater would receive that, and at the same time then it will go into transmit to rebroadcast that signal out again. So that's where we will go into what's called a Dualplex filter, where one antenna is shared between a transmitter and receiver at the same time. And if you haven't seen the other videos that I've done on Duplexer tuning, have a look at those. That'll give you some idea of what Dualplex is about. And then obviously we need to check the transmit parameters, the transmit side. So on this radio, this is a simplex radio, which means it can't transmit and receive at the same time. That's why we have a press to talk switch on the microphone. But radio repeaters can transmit and receive at the same time. Indeed, there are some radio systems around the world, like in ambulances, etc., where they do have Dualplex, because they use multiple radios all connected in a box to a Duplexer, and they have like a telephone style handset, and they can use the radio then to as a phone, basically as a transmitter and receiver at the same time, so that you can make radio systems that work that way. And in the case of the ambulance services, they use it for passing patient information while they're en route to hospital with a patient, so they can talk and receive at the same time on some of these patient radio systems that they have in the ambulance, as well as have a simplex radio mounted on the dash of the ambulance, where then they can talk to ambulance control directly. So some ambulance services, for example, can have multiple radio systems in the ambulance. They can have obviously repeaters in the ambulance, so that when paramedics get out the ambulance, they can use a repeater to extend their radio range if they're going into mountainous terrain or into subterranean environments, or where a paramedic needs to relay information back to another paramedic or ambulance personnel that's not located nearby. They can use the ambulance as a rebroadcast repeater. They can also have a patient transport full duplex set up in the back, so that while the paramedics in the back, they can be talking while they're en route to hospital to the accident emergency ER department at hospital, giving vital information about patient statistics. Data from the radio that's collected from medical diagnostic instruments within the ambulance can be transmitted over a data channel at the same time, and there can be transmitting and receiving simultaneously in full duplex to the hospital ER, and whilst the paramedic in the front then can be using a dash mounted radio to talk to ambulance control, letting them know that they picked a patient up and they're en route to hospital, or they're going to an incident, or the arrived incident, that kind of thing. So you tend to find that radio will be a simplex radio, but the patient transport one in the back might be duplex, so they can use it as a telephone patch type thing. Often they'd have a DTMF keypad, so they can dial phone numbers and things like that, and they'll get telephone patched through a base station into the hospital's PABX telephone system. So there's all sorts of different radio schemes and scenarios, and that's really what Duplex test takes care of. It takes care of radio systems that can transmit and receive at the same time. And so even though this is a simplex radio, when I key up, this is still generating a signal out to the radio, even though the radio can't receive it while I'm in transmit. So the moment I press to talk, now it'll be reading the transmit parameters. And obviously when I speak into the microphone, 1 2 3 4 5, we can see that. Now what we can do as well as part of this test, we can expand. So there's a Dualplex test TX, so then we can go into separate tests. So we've got a Dualplex test TX, so all that means is that it's still sending a signal out while we're doing this test here. It's still generating a signal, whereas on the receive side, it's the RF signal generator still working, whereas when we're doing separate TX and RX, when I press the TX button, it's not generating an RX signal anymore. When I press the RX button, it's obviously not looking at the TX side anymore. But on the Dualplex test with TX, it's still generating a receive signal out to a radio, even though we're not actually using that measurement at the moment. It's just so that with this being a simplex radio, we can still send a signal to the radio while we're still in the transmit side, and that's useful for when we're measuring duplex radios, even though this is simplex. And then we can do further analysis of a transmit signal in duplex mode. We've got the usual thing, we've still got the spectrum analyzer. We can expand on the spectrum analyzer to make it full screen if we want. So we can see that we've got those capabilities still there. Likewise, if we go back to duplex, and we go to the receiver testing side, Dualplex test RX, then the transmitter can still key up, and it won't make any difference, because obviously we're just looking at the receive side and ignoring the transmitter side. And then back to Dualplex again, then we've got the split screen again. So obviously Dualplex test under RX as well gives some more functionality down this side. Again, we can generate signals, and we can also switch between Dualplex TX and RX as well. We can do that there and flick between them. So that gives you a little rundown of Dualplex. So another thing about Dualplex as well, which you can get an idea of when you're doing a Duplexer filter which connects to the radio transceivers, a receiver and a transmitter in a system, and then obviously we've got the common antenna output as well, which is on the side here. That when we're aligning this, which is gone into on another video that I've done, again if you look at my channel you'll see there's a video on how to tune duplexers. The test set allows us not only to do the test that I've just shown you, but it allows us when we're doing testing with radio receivers, is we can do two different types of tests with Dualplex. We can connect on what's called a single port, where we're transmitting and receiving on the same port, to the antenna connection on a Duplexer output, and that will then obviously test the paths that are split individually in the Duplexer. We have a transmit side and a receive side, and they will obviously then go on to the appropriate radio receivers and transmitters. Also, without the Dualplex, because some systems don't have a Duplexer included within the actual system's cabinet, that's external to the repeater for example, then you can select for example a path where in this particular case we have the signal input, if you like, coming in on the 1 watt port. So this is where we've got to be very careful when we're doing Dualplex testing, and the signal generator output is on the high power N type port, because obviously we've got 1 watt here. We wouldn't want to be transmitting in on this port. Obviously if we've got 25, 40 watt whatever transmitter going in here, it's going to blow the test set. So you've got to be really careful that if you've got a radio system that doesn't have a Duplexer at that stage, you don't connect the transmitter to the 1 watt port and the receiver to the high powered port. If anything, you select it the other way around, so the receiver is on the low power port and the transmitter, the signal coming in, is on the high power port, and that way you don't damage the test set. It's very easy to make that mistake, and you've got to be so careful when you're setting the test setup that you don't inadvertently connect something to this port here, because it could cause damage obviously, the transmitter side. So normally in this context this port will go to the receiver because we're generating a signal out, and then that side will go to the transmitter, and that's where we would measure the signal prior to introducing a Duplexer filter. Now I won't go into too much detail in this video about the Duplexer filter because that's covered in other videos on my channel, but basically in a repeater system where you have a separate transmitter and a receiver, they will connect to these ports. The transmitter signal would come through the Duplexer and then go out onto the antenna port, but the receive side of the filter with these tuning screws would be tuned to reject the transmitter frequency. So no power from the transmit side can make it out onto the receiver side, and because obviously it would damage the receiver. And likewise the receiver side obviously, as I've said, rejects the transmit side rejects the receiver side, and then between the two sides it makes sure that the filter allows the transmit signal to pass through, and obviously the receive signal from the antenna to pass through to the receiver port, whilst giving isolation between both transmit and receive ports. So that's the idea behind a Duplexer filter, is that it allows a radio system to transmit and receive simultaneously by using a common antenna, and thus prevent the transmitter from damaging the receiver. Now This particular filter is a VHF one, I believe, although I might be wrong there. Let's have a look. Frequency megahertz, yeah, 159 to 164. That's got a particular split as that, and that's again something which a lot of people don't realise with Duplexer filters, that depending on the design of the filter will depend on the frequency split. So if you're doing a duplex system with a repeater, if a split's too narrow, then some duplexers can't cope with a narrow difference between the transmit and receive frequencies, and so therefore duplexers need to be chosen for the correct frequency banding we're using, so the split. So a 1.6 megahertz split, for example, would mean a higher Q cavity would be needed, and the narrower the split, the more expensive a duplexers become, because they need more resonance, more Q in the filter chambers. And the types of filter, there are different types of filter. There's band stop, band pass, band reject, there's notch types, different types of duplexer filter employed for different reasons. Whereas a diplexer is where you split radio frequency bands up. So for example, you would have a receive side on VHF, say 160 megahertz, the transmit side on UHF 440 megahertz, for example. And so you could use two different radio systems using one antenna. That would be a diplexer, whereas a duplexer is an in-band filter, where obviously we're using a UHF radio in this case, system that's duplex in that scenario, and we would say be transmitting on 430 and receiving on 440, and vice versa. So we've got a 10 megahertz split in that case. So you need to choose a duplexer filter that's capable of resolving a 10 megahertz bandwidth. There's no good choosing a 10 megahertz spec duplexer that's a 5 megahertz split, is its lowest resolution it can go to, and therefore you then try and use it in a 1.6 megahertz split application. It won't do it. It's not designed for that, so you'd run into issues. So you need to make sure that you choose the right duplexer for the job. But that's just a little rundown on that, and that's why we'd use these different ports for doing various things like that. And yeah, so there's all sorts of little bits that you can get into. It's quite interesting, some of the things that you can do. Right, we'll move on to the next section. Okay, the next feature that I'd like to show is tones. Now in tones menu, there are lots of different tone standards that you can go into. So we'll just have a look at those just in this screen. So first of all, on the left side we've got ctcss. That's basically for all the continuous tone coded Squelch system. ctcss is commonly used throughout the world. We can set things like the level of deviation, what mod gen it's going to be using. We can have a tone on or off. We can select a tone where we have to put in the tone number, so 30 equals 167.9, so I'd have to enter in 30 for example, and then press the enter button, and then it would generate that tone at 167.9. We also have outside of this, we've got, if we go back into tones a second, I've just come out of that screen, we have DTMF tones as well, so we can actually enter in using numerical keys or whatever a DTMF tone sequence. We can put in a predetermined sequence if we want, and as well as that, in duplex mode or in TX mode, you can decode DTMF tones that's sent from the radio as well. So this basically will give you errors of tone. So if a DTMF tone encoder in the radio is transmitting incorrectly, it would go to an error in here, and it would tell you how far off frequency each tone is. So if I enter in any of these, so I could do, you know, so I could generate DTMF tones. If I want, I could put in a tone sequence. So I think tone mode, change sequence, and then I could enter in, for example, use data keys. So I could do that. And then now that I've entered that tone string in there, then I could press I think it is enter, and then tone mode, tones on. So that's obviously sending it to the radio. Now down at the bottom here there's expand DTMF decode and expand DTMF generate. So if we go to expand DTMF generate, then you can set up the deviation, the tone deviation, and obviously the tone frequency plan, etc. You can go into quite a lot of detail there about locking and unlocking levels, particularly if you've got some weird DTMF tones that you've decided to use that are outside the international standards. You can obviously alter things to do what you want as well, and then there's obviously tone mode there. So if I go back to expand off, likewise if your radio is transmitting a DTMF tone as well out from the radio, then I assume, I don't think this radio is set up to do DTMF, but you can send a tone to the decoder within the test set, and it will display which keys you've pressed on here, and it will tell you what high and low frequency error there is. If there's any error, it will list them down here, and that will then show you that. Now there's obviously DCS, digital coded squelch, as well. What DCS is, it's a digital version of what will be the analog form of ctcss, and so basically we can set up again the same thing, deviation of the mod gen 3, the polarity type as well, because it's digital. We can change the polarity, and obviously as part of this we can, if I can get the camera to focus better, I think we can set up a code. Now there are quite a lot of codes. There's more choice on DCS than there is on ctcss, so we can go on to DCS on or off. It'll start sending a tone out. We can do decode level as well, normal mod gen, and you can set up the code as well and put the code in. So we can do that. We've got a bit rate as well, we can change the bit rate, and then we've got the invert, normal and invert. You can select between that as well, so you can do quite a bit with it. Now if I go to, we've obviously looked at sequential, ctcss, DTMF, pocsag would be what's used for paging, so we'll have a look at that next. But what I'm going to do first of all is I'm just going to try and set up the DCS side on the HP radio test set over there, and we'll see whether we can decode the DCS. Okay, I've set up a measurement now where we're going to transmit a DTMF tone to the screen, and if you watch in the top left hand corner where it says symbol SYM, and I press button 1 on the test set, obviously it's giving us the key 1 which I pressed. If I press button 2, it gives you the frequencies and obviously any errors or whatever. 3. So that's proving that obviously the DTMF side's working. So that's how we've tested the DTMF output on the radio test set, so that we can obviously decode it on there. Now as for DCS, I couldn't find on there the tone standard for DCS. Doesn't appear to be one on there, so I think we might have to do some magic. We're trying to use a different test set for that. We'll have to use the 2968 that I've got, switch that on and just see whether we can get the DCS tone to be decoded at the other end as well to demonstrate that. Okay, so I've set up a test now where we're generating a DCS signal out and we're measuring it on the IFR 2968 radio test set. As you can see there, I'm sending out code 50 from this test set, and we are decoding it successfully there. Obviously there's two places where it found it, but code 1670050. So as I change that, obviously that waveform will change as well. So that's the DCS. If I change the code or switch it off and then switch it back on again, then it's finding it. So that demonstrates the decode capability on the DCS side of things. Now on the HP8920, interestingly enough, it wasn't decoding it as in giving you the code like the Marconi IFR does. Basically all that was doing is it was just displaying the data bits here, but not actually displaying the code, because this is actually a different digital standard. It doesn't seem to have DC SS on it. It's got ctcss, which is a different standard, probably more American standard than European, but obviously this is European standard, is DCS. So that's a little rundown on that DCS. DTMF we had a look at. Now we'll look at Selcall and pocsag paging standards. So as far as transmission is concerned, where we're transmitting into a test set with DCS, I've set up another test here where we're going to be sending a signal out from the 2968 to this 2966. So if I send code 777, then it decodes it and finds it there. So that's obviously sending from what is emulating what will be a transmitter going into the test set and then decoding DCS. So that shows that working. Okay, so let's have a look at the next section in the tones menu now, which is signalling, and we can have a look at these standards down here for Selcall, which is commonly used across the world with all sorts of different services, from emergency services through to private mobile radio users, etc. So there are different tone standards: ZEA, DZVEI, ZVEI, CCIR variants. There's obviously CC, EIA, and user defined as well, where you can define your own tone sets. But for example, if we use EIA, and just to demonstrate what Selcall is, if we were to enter the sequence and just put in a radio call sign, for example, it could be anything, and then enter that by pressing the enter key. So the sequence is there. We're in EA tone standard, tone mode, and then click, if I just turn the volume up on this radio, so that's what it sounds like. And then of course, using different standards, they all have different tones and different tone lengths. ZVEI, CCIR, and then of course there's EIA. That's more quicker. But in the UK, EA is the more widely used tone standard, but they can be used any of the tone standards in the UK as well. I've certainly done radios in the past that have got these tone sets on. And so if a radio was programmed for auto acknowledge, for example, then it would receive a code, whatever call sign it is, and then it could rebroadcast the Selcall tone back and acknowledge code back. So that's another way. The useful feature of having Selcall on radio systems is that it not just only calls a radio and opens a radio up, but it actually can force a radio to transmit a message back to confirm it's received the call. A typical example of that used to be employed here in the UK was with the ambulance service. And if somebody rang, you know, a 999 because they're having a cardiac arrest or a heart attack, something very serious, then what they would do when the control wanted to send a message to the radio, be it in an ambulance that was mobile available, or in the ambulance station, they would have a radio that would be connected to a relay, which would then sound a klaxon or a bell, a siren, having flashing strobes around the building. And what they would do is they would send a Selcall tone out, and it would alert the radio, and the auxiliary connections at the back would close a relay that would energise a klaxon or whatever. And then of course the loudspeaker from the radio then would be unmuted, and they could talk then over the tannoy system in the ambulance station to the paramedics on the way to the ambulance, or paramedic fast response car, and be actually divulging patient information verbally while they're actually going to the vehicle, like location, where they're going to, things like that. And the nice thing as well in ambulance scenarios, when they're out and about dropping off and collecting patients to hospital and doing the routine emergency calls, they can send different types of Selcall tones through, and you can program different alert systems in the radio so that there can be non-emergency calls and then emergency calls, and you can distinguish between those with the alert type. You can control things like the tone that the radio gives out when it receives a Selcall tone. You can also make it do different things as well, like open up the receiver and maybe go to a different radio channel to set up a voice call. You can do all sorts of things with Selcall. It's a very useful tool to have. But from a control perspective, if you've got loads of mobiles out there and you want to send a message out to everybody, for example, because there's an incident where you want other vehicles to avoid that area, then you can send a group message out, Selcall, and you can actually get messages to appear on the display, or you can open everybody's radio up to then speak that message, and then you can then send another Selcall tone out to close the mutes on the radio. And as well as that, it means that the radio channel's private, because when you want to, as a control room, speak to a mobile, you can just send their call sign out and it'll activate that one radio, and then the speech channel will just be used between that radio and control, so it keeps conversations private. And as well as that, also on the radio there'll be a press to talk button, a request to speak, and when they press that button, it will then send a Selcall tone back to the control room, and that particular tone set will equal request to speak, and the software that they run in the control room system will be able to decode that tone set, and it will come up on the radio operator's screen, ambulance or paramedic, whatever call sign, request to speak. And so they can use status messaging through you know, through Selcall. And that's the thing about some of these classic analog systems, is that everybody thinks, you know, that's coming into radio today, the modern advances that we've got digital radio and DMR, that all this status messaging is all a new thing, and it's been around for decades. You know, it's been around, you know, in 1970s, so there's nothing new really in radio. It's all been invented before, but that's a typical example of Selcall. So what we'll do, we'll connect this instrument up now to the Marconi test set over there, and we'll emulate a Selcall tone from there as if we were broadcasting on a radio to this test set, and then we'll decode the tone that we're sending. So we'll show that next. Okay, so we set the measurement up now. So in the transmitter test, we're generating a signal coming in, which the test set's picking up, and now if we go to tones, and we select EEA tone standard, which is here, and I've set up a measurement here where we're using EEA, and so in theory when I send that signal now to the test set, it should decode it, because we've got the TX sequential tones decoder on for EEA. So there we are. So it's sent the correct tones and everything. Likewise, if I use DZVI and we change that to DZVI, and then we'll clear the sequence and send the tone again, which I'm sending 1258789 6. So there we are, decoding quite nicely. So that gives you a little rundown of that. We'll try the other tone standard now, ZVI. Clear the sequence again, and then it's decoded it again. So that's just a typical example of, you know, I'll just turn the RF gen off on the other test set. There we go. So that gives you a little rundown of both encode and decode on using Selcall under the tones menu. Now, if I go back to tones again, we'll go back to receive, receive test, and then under tones. Now there are differences between the receive and transmit side with the tones, because you'll notice when we're receiving, as in a signal generator, sending a signal out, we get additional features that come up on the screen, one of which is pocsag here, and pocsag stands for Post Office Communication Sub-Advisory Group, and it was a specification that was produced in the UK by the Government Telecommunications Office many years ago, the GPO as it was known as, and they produced a technical specification for paging systems in the UK, and pocsag was one of them. And there are different standards as well within there, but if we go to pocsag, and we can put in paging frequencies, baud rate, the actual polarity, we can type in a message as well for paging, and it uses a unique kind of FFSK, fast frequency shift keying, where it instead of modulating the carrier with information, what it does, it shifts the carrier frequency. So for example, logic 1 would move a carrier, shift it plus say 4 kilohertz. Logic 0 would make the carrier go back to center again, which would represent 0 level in the logic, whereas logic 1 would be plus 5, 0 would be the center frequency, and then minus 4 kilohertz would be a logic 0 as well. So it would confirm either way what data bit it was, and parity bits as well. So that's how it would modulate the carrier. We'd start at 0, go plus, then we'd come back to 0 and then go minus again, and then back to 0 and plus again, and then that's how the mark space ratio of that would equal the binary information, the logic data, which would then obviously be reconstituted by the pager, and then it would pull that data off. So that's what we're going to look at next on this. We'll generate a signal into the radio that we've got, the test radio. So if I change the RF gen frequency to 145.5 megahertz, and I increase the RF gen level, which we've got there, we'll connect that to the back of the radio, and then that should receive a signal then on 145.5 megahertz. So that's what we're doing now by connecting the rather awkward coaxial cable up to the back of the radio. And we'll turn the volume up now on the radio, and in theory I should be able to put a RIC code in. The RIC stands for radio identity code, and there's a message there. That's alert only. And you can select different types: beeping, text message, then send that. The preambles you can set up as well. So that gives you an idea. Now with pocsag, because I used to repair pocsag transmitters many years ago for certain customers, and when you're under TX test on the, if you come out of that, go back to TX test, back into tones, you'll notice when you look at the screen, pocsag is missing, and that's something that the test set doesn't support, where you can decode pocsag in the tones menu. You can encode it to send it out to a pager, to test a pager, but if you're maintaining the other side, I like to see that pocsag decoder. And I did have a radio receiver with some software which you can use, like GNU radio or ACRF from Great Scott Gadgets, things like that. They allow that capability to decode. But it's just a shame that the test sets, and you won't find many test sets that do decode pocsag. They'll encode it but not decode it. But when you're doing transmitters anyway, pocsag transmitters, you don't actually align them by sending codes out. What you do is you align them where you'll move a frequency. You'll put in like a 1200 Hertz baud rate, a square wave, for example, 1200 Hertz, which is like your guard tone, and then you'll adjust the transmitter to move the RF carrier one way or the other. You'll measure the frequency shift of the carrier, and you'll also put in logic levels as well to move the transmitter upwards in frequency to represent a logic 1, and also minus the frequency to represent a logic 0. So the alignment procedures on pocsag transmitters or paging transmitters are totally different to what they are on the standard radio, but that's the reason why you don't get the decode in there, because there's no need for it. And if you're going to check the paging side of it, then you may as well do it with a pager anyway, so it defeats the object. So I can see the sense in not having the decoder there, but I would like to have seen it, so that at least then you could send a tone set to it from a paging transmitter and then read it on there. But there are other means of being able to do that, but for some reason Hewlett-Packard, Roden Swartz, Marconi IFR, Aeroflex, many other test sets, I think the Motorola ones are the same as well, where they don't decode pocsag, they'll encode it. So that's a little rundown on pocsag for paging. So next thing I just wanted to demonstrate under the transmit side of the instrument is the spectrum analyzer, and you can get the spectrum analyzer to appear just here in the screen, and you can also expand on that as well, and you can adjust the reference levels, how many kilohertz per division, single and repeat. There's quite a lot of other functions as well. You can put markers on as well. You can do quite a bit with the spectrum analyzer. So if I transmit, and then we can adjust the reference level, and we can see the mod on it as well. 1 2 3 4 5 5 1 2 3 4 5. So that's there, 1 2 1 2 1 2, and the RF power as well in dBm, and you can obviously move a marker. So if I move a rotary control, I can, as you can see there, move a marker get it right up to the top, and then we can measure that level, and we can change the resolution, bandwidth, the dynamic properties of the spectrum analyzer, and we can look at harmonics up band as well. So we can go right in on the RF carrier, or alternatively, you know, we can just can pull out as much information as you want, and check for any harmonics as well out of band. So there's all sorts you can do with it. It's quite a nice little spectrum analyzer. So very nice little tool to have. So we'll go on to the RF test option now, and we'll review that next. Okay, the next stage that we can go to is the RF test. So from the TX menu or RX, whichever screen you're in, we can press the RF test. In there we've got two options. We've got the RF input output test and the RF single sideband test, which we'll look at a bit later. But in the RF test, we can set up there basically a measurement using these two ports, where we can measure signal levels passing through a filter, for example, or an amplifier, that kind of thing. Now, what we can also do in this arrangement is we can also sweep filters, and how we do that is we once we're in RF test mode, we select spectrum analyzer, then we expand on that, and then basically there's a track gen option just there for tracking, and so when we select the track gen on, we can actually set up an RF level. Now we've got the signal coming out of this port and then being received on this port here. We've got a link cable that's just linking them, so we can set up the track gen. Now if I set the RF gen level, which is under, I think under RF test, RF input output test, RF gen level 0 dBm, I'll try and go for that. Might have to switch these round the other way to get 0 dBm, because it can't achieve 0 dBm on the high power port. Right, so we've got 0 dBm coming out of here and going in on there, and what I will do now, we'll go back to what is a spectrum analyzer, expand, right, track gen on, and so we just need to set that now for the top line with marker 1, which is here, is at minus 1.5 dBm. So we'll just see if we can get that as close to the top line as we possibly can. That's good. So reading our reference level at marker 1 is minus 1 dBm, which would equate for the coaxial cable. Also, because if I grab the coaxial cable, and it can change its performance slightly. So that's marker 1 there. Now what I can do now is we can connect the filter, because the primary reason for doing this is to adjust the levels that are coming in and out through the RF in and out, to calibrate the track gen, so that we've got the top line as 0 dBm, which is our reference rule of thumb, and then we can then disconnect this cable and then connect the filter or the RF instrument that we're going to be looking at. So we've set that up now. So if I connect up the Duplexer filter, and then we can alter the bandwidth of the spectrum analyzer, then to look at the overall performance of the Duplexer. And so I can then set a center frequency as well. At the moment marker 1's 147 megahertz. If I move marker 1, which is there, we can see that it's more or less centering the screen. Now I could pull that apart a bit more, and then we can go center frequency, so I can do TX frequency. I think that's it. We can move it more or less back towards the middle now. Oops. So then we can look at the notches, the dual notches for this filter. And then we can just home in a bit more. So that's the response of this filter. So what we're doing is we're measuring both the transmit and receive side of the filter, and the antenna port is into a 50 ohm load. So we get both sides of the transmit receive section of the filter, and as you can see there, we're down at minus neg 65 dBm on these notches. So that just gives you an idea of how we can sweep a filter. Now you can obviously adjust the markers as well, move marker 1, and then using the rotary control you can obviously move the marker 1 and measure the level there, and then you can then move marker 2 as well if you wish, and then marker 2's details are displayed at the top, so you can get the minimal level there, which is neg 60 dBm. So that's all there. So you can do quite a few performance measurements using this TrackGen and spectrum analyzer. It's quite a useful little option. Obviously you can use it for sweeping anything, bandpass filters, you know, RF tuning circuits, pin diodes, helical resonators, Duplexer filters, crystal filters, anything really you can sweep with the RF sweep generator. So that gives you an idea, a little overview of what we're dealing with there. Right, we'll go on with the next test. Okay, so if we go back to RF test again now, and we can have a look at the single sideband test. So we can select that. Now in the SSB mode, obviously for the transmitter side, for the receive side you generate AM, and then you can move the frequency up and down to represent upper sideband and lower sideband. But for transmitter obviously you need to be able to use the SSB option that's in this to decode the SSB signal. So basically we can output modulation if we want as a fixed level from the AF gen output. That could be fed into the microphone circuit of an SSB radio, for example. We've got the RF power measurement as usual. In this particular case we don't need to generate AM for simulating the receive side, because we've got an SSB for the receive side as well. But you can do that on other test sets if you don't have SSB option on and you want to test an SSB receiver. You can use AM to do that. Now in this particular one we've got upper sideband and lower sideband selection here, USB and LSB. A little bit difficult there I think for the camera to see it, you can just about see it there. So that's upper sideband or lower sideband. There's a band pass as well, and all the different filters for the audio, for the demodulation. We've got distortion measurements. Obviously we've still got the Cyanide, signal to noise and distortion. There's an audio analyzer that we can bring in as well if we want to do that, or bar charts. We've got the scope option as well, and then we can expand as well on that if we want to. So lots of features that we can go into. In addition to that, under TX, obviously we've got the same again, except we're measuring TX power, and we've got upper sideband, lower sideband again, but this time we've got CW for Morse code, CW, and then of course we've got the same distortion. We have a suppress feature as well, so we can suppress the sideband as well for USB, LSB and CW, and then we've got the spectrum analyzer, and we've also got an S-band analyzer. Now if I select the sideband analyzer, then we can reveal more information about the sidebands as well. That'll be quite useful, that, for particularly tuning radios precisely with regard to the sideband characteristics, where you can pick that out. Also under there with the spectrum analyzer, you can check for harmonic content as well, because obviously with sidebands and the power that you're broadcasting at as well, you need to keep an eye on the side, on not just the sidebands but the harmonics as well, so we can do that with the spectrum analyzer. So yeah, fully featured little test set there for the SSB single sideband, upper sideband, lower sideband CW testing on both RX and TX. So that's quite useful little feature. Okay, so we'll have a look at the AF Gen now, the audio test. We can get to that from any screen just by pressing the AF test button, and then we've got the audio input output test. We can set all these generators up. There's 3 gens that you can actually set up if you wish to use them, and then of course we can send a signal out through the AF Gen output, which I'm doing at the moment. I'm sending 100 millivolts out at 1 kilohertz, which has been displayed there on the oscilloscope. So that gives you a demonstration of the AF Gen out. What's nice as well about this particular instrument is that you've got the DC-AC couple function on the what is the AF in. So if we were to connect a scope probe here, you can actually use it as well in your fault diagnosis work for fault finding with voltages in circuits, and you can change that to DC by pressing that button. It toggles between AC and DC, and then you can read DC voltages. You've also got the oscilloscope as well, and which you can set the position here as well with the potentiometer, the scope position. But you've got that capability as well as selecting different filters, using AC or DC couple for measuring voltages and waveforms. So quite a useful little feature. So it expands it out of the arena of just radio telecoms. You can use it obviously for hi-fi measurements, measuring audio circuits and audio amplifiers, microphone circuits. If you're building something that needs to be tested, that's an op-amp circuit, for example, for audio amplification or audio filters, you can test all that here. So that's a nice little function that that you've got. Okay, so we're now going back into what is AF test from any of the screens, and then we can look at the full function multimeter, and in there, this is where we can use these ports here. We can measure voltage directly into here. Now the rating is written on the front. If I remove those just a moment and we take a look at that, we're looking at 300 volts maximum on either of those, volts and ohms and amps, 10 amp maximum between these 2 ports here. So we can obviously measure that voltage there, and ohms, continuity. We can measure AC and DC volts there, DC amps, AC and DC amps on these as well. So if I just zoom back out again, we've got a reading there. We've got a continuity option as well. So if I plug these probes in just for demo, and at the moment I've got a power supply on that's doing about 13 volts DC roughly, so we'll just connect up there just to demo that. So again, you know, it's quite a nice resolution, wind the voltage up and down, etc. We've got the bar graph, obviously. If we're measuring current amps, which I can do that, I can turn the current limit onto the power supply, and then we can increase the current. So we'll put about an amp in, I'd say, and then we can read DC amps. So I've got the current limit on the power supply set to about 1 amp, so reading that quite accurately. And then obviously if they were inverted the other way around, that'll be reading minus current as well. So that's quite useful, particularly for when we're doing measurements with radio transmitters, how much current they're consuming, which is quite useful in that measurement, because in the service manual it might say when it's doing 25 watts it should draw 4 amps or 4000 milliamps, so that you can check the current consumption on the meter, meets the specification of the radio. It could be then, if it doesn't, that the transmitter power amplifier section is retuning, for example. We've got the ohms, so if I touch the probes together, then it'll read obviously a dead short, whatever the ohms of the leads are. There's continuity as well, which if the volume's wound up, we can get a beat as well. So it does all sorts of little tests, basic multi-function multimeter really. It doesn't do capacitance, doesn't do sort of diode tests or anything like that really. It's just volts, ohms and current, basic stuff really. But it's great to have that sort of thing built into the instrument, so you're not messing about with separate meters and all the other shenanigans. So quite an open you know, instrument for that kind of thing. I like how it says open and close as well when you, so if you've got the volume down, sometimes the volume will be down. If you short the probes out, oh, you can still hear the tone, but then it says open. So it's quite a natty little tester, quite like it. So that's a little rundown of that. Then of course you've got hold ranges as well, which you have hold, automatic or repeat, so you can obviously make a measurement and then hold it. You can do that, so that's there, and then it'll find that maximum level and then it'll hold it there, so that's quite a useful little feature. And yeah, nice little test instrument that for using with everyday fault finding on, you know, radios, etc. Now on with the help setup menu button, which is just here. We can restore to factory settings, so when we press that it'll go through this sequence of restoring itself and resetting. So I suppose that's the equivalent to the green button on the Hewlett Packard test that you can see down the top right. So it does its reset back to where it was before, but in there we've got all kinds of configurations. So we've got help screens as well. We've got user configuration, user calibration, demonstration features, software version numbers, and then obviously we can go into greater detail on there. So for example, if we look at help on other functions, then it's got an entire library of help information in for spectrum analyzer, for example, how to perform measurements on that. For the track gen, there's all kinds of setup options in there that if you read the text, it'll guide you on how to set those measurements up. Then we've got user configuration, and then in there we've got another sub menu which is settings and measurements configuration, instrument I/O port configuration, miscellaneous setups. So we can go for the first one, settings, and then of course we get other sub menus as well, where we can set up all kinds of things. So for example, I can select that, and then it'll tell us whether it's 600 ohm or not, and you can go really in depth into it. There's quite a lot. Digital systems setup, sound and distortion parameters, versatile tracking generator setup. So if we have a look at that, for example, then you can set up whether it's a normal track gen or something different. You can set up your doubler. There's all sorts of different things you can go into there. Then of course there's TX measurement setup as well. You can set up counter resolution, so you can go down to 1 Hz resolution or 10 Hz resolution. The average counts of what it does in the measurement, so you can increase or decrease that accordingly for different accuracies. And then we've got all kinds of different settings in there that we can adjust to sort of customize the test set to the best capability, what you want from it. And that's a nice thing about this test, there's so many things you can do with it. It's very advanced in that sense. We've got miscellaneous setup options as well. You can set up the display screen savers, shut down display time and date, display time and date, enable and display software options, so you can do that. It'll tell you what's installed on it and what isn't. And then of course there's user names as well. You can put names in and things. User power on setup configuration. You can do quite a bit there as well, which I've not really had much involvement in doing really. Language select as well, so you can select obviously for different countries. We've got English, we've got, if I can zoom in on that, it's very difficult with that screen to see it, but we've got English, French, Dutch and Spanish, so that's quite handy. So if you buy one of these test sets, a multi-language support, so it's not all in English all the time. So it's obviously made for different international markets as well. So there's quite a lot of things. The instrument I/O configurations, you can obviously set up your remote control, GPIB, your RS-232 port, your printer port. On the subject of printer, you can actually do a copy screen, and then when you do that, then you can press copy again to copy to the printer, or press delete to remove this message, and any other key to cancel. So you know, you can print the screen, and that's the same in any measurement really. So if we go right back to that screen, for example, Dualplex, and you want to copy that, then of course you can then print off whatever measurement that you're making to a printer as well. So and again, you can store that particular test as well if you want in one of the memories. I think it's 20 memories, which we looked at earlier. So there's quite a lot that you can do. I think one of the things that I've not dealt with was I think the increment. We did use that a little bit earlier, but that comes in use for when you're doing RF gen frequency, then increment button, and that then you can set up an increment, say of 12.5 kilohertz in this case. So then when you press the up and down buttons, you can jump up in 12.5 kilohertz steps as well. The rotary control, you can set that to how fine that will be, and then you can do the same with RF gen level as well, increment and make it 10 dBm for example, and then every time you press the level up and down button, then it'll adjust that as well. So quite a lot really. So that sort of shows you more or less everything on the instrument by now. I think we'll turn it round and have a look at the back, and we'll show you what features and options there are at the back for connectivity there. Right, we're around the back of the instrument now after we've nearly pulled our arms off trying to move it round, because it's that heavy. Is this test set? It's a very heavy unit indeed. It's a lot heavier than a Marconi 2955 is, put it that way. So just on the side here, I'm not sure if we can see that very well on the camera. Just see if I can get some more light on it. I don't understand why manufacturers do this, where they put the power switch here on the side. Trying to reach down the side of this instrument with your arm and fiddle about trying to flick this switch here is a real pain in the backside. I don't like that idea. Roden Schwartz did it with a CMS 54 radio test set, which you'll see on one of my other repair videos. But putting the switch at the back here is a nightmare, because if you've got it inset into a bench or it's higher up on a shelf set back, having to keep switching this on and off is not really a desirable thing. And trying to reach down the side, it's a very long test set. It's almost like a 3/4 of an arm's length just to try and reach in. And then of course if you've got a bench in front of you, you know, you have to do some kind of acrobatics to try and get your arm round the hand round the back here and feel for this switch. It's not exactly a big massive rocker switch or a push button that you can easily find, and if there's other cables down here, then you know it's difficult to try and feel for that unless you know where it is, because you can't see it. So anybody who's new to the test set or trying to figure out how to switch it on, you know, would perhaps struggle with that for the you know, the uninitiated. Now oh dear, my knees. Right, so that covers the power switch, which I'm not fond of. I didn't put a power switch on the front of the instrument. Goodness knows why. It would have been easy to do in my view, but there again, they've designed it for that particular reason. So on the back, just we'll go from sort of left to right and then down as we go across. We've got the big power supply unit here on the back with a fan, obviously. It is generally quite a quiet test set to run. Some test sets sound like in a wind tunnel when they're switched on, others are quite quiet. I always found the Marconi instruments to be reasonably quiet. I think the Hewlett-Packard radio test sets are very loud, very noisy. Certainly the Anritsu test sets that I've got are very noisy indeed. You certainly know they're on, and so you do with the Roden Schwartz to some extent. Although I must say the Roden Schwartz test set is probably as quiet as the Marconi's really. So yeah, I think some of the Marconi test sets as well can be a bit loud. The microwave radio test sets have bigger fans in, and they can be quite loud. So it varies from test set to test set rather than manufacturer to manufacturer. But this is quite a quiet test set, is this. So we've got the GPIB general purpose interface bus, IEEE standard on there, which is used for controlling the instrument with remote software, auto testing, things like that. We've got the options chart. So this is fitted with, this particular one is fitted with option 9, I think it is. We've got an accessory port at the back. Now we can use this for further auto testing as well. There's details of what these pinouts are and what they can be used for. Normally the accessory socket is what's connected to Marconi accessories, which are fitted underneath, like system trays for doing different things or supporting different radio networks. We've got the 9-way RS232 serial port on the back as well. It's standard serial protocol. We've got an external reference in signal here. So if we're running an atomic frequency standard, a cesium or rubidium frequency standard, a GPS clock, an off-air sync clock, you know, anything like that can connect in there, which will then, within the settings within the instrument, you can then decide to point the reference to an external high accuracy reference, which is more superior than the internal reference. We've got an AF port on the back here. Now if we look at the symbology, that's an out. So we can decouple AF that's been measured in the instrument out of here. Likewise we've got D mod, again an outgoing symbology on the D mod, so the off-air D mod can be done as well. And then we've got the IF intermediate frequency output as well, which we can use in this case to pass off to other instruments such as spectrum analysers or other high accuracy instruments for measuring you know, the content of the IF signal. So we can do all the measurements with that. Now down here, just under the power switch on the what is the right hand side of the instrument, we've got a VGA SVGA output for obviously for an external monitor, and that comes in very useful for connecting to other displays, be it TVs or LCD monitors, LED monitors, that kind of thing. These days a lot of the monitors that we have are HDMI, but you can get VGA to HDMI adapters. You can also get some of the older monitors, or even some of the new ones, like the HP ones I've got here, do come with different sets of leads. They'll come with a lead that connects to VGA, but they'll also have an HDMI or DisplayPort adapter, so you can connect in there. If you don't have a monitor that supports VGA, then you can always buy an adapter which plugs into the VGA port and then converts it to HDMI. So that's about it really for the rear of the instrument, apart from on the very far right here, hidden away, out of sight almost, is the parallel port for connecting directly to a printer, and I think it uses a standard FX80 printer drivers for doing printouts, but I think you can configure it as well for HP and load drivers on for that as well, or you can configure your HP printer in a different way to accept that kind of print output for an FX80 standard. So that's a little rundown around the back. Now what you can also do with this instrument is measure the signal off air using an antenna onto the low power port. Now if we select the low power port, I've just got a bit of makeshift solder there plugged in. We've actually got an option as well for the off-air test, which is this option here, which you can see second up from the bottom, that off-air test. So if we select that, we can then do an off-air test. We can then put in a frequency and try and tune to it. So for example, I could put in a radio station in the broadcast band, for example. So I could let's just do this now. I think it's TX frequency. You have to press TX and then frequency, and then if I say set it at 98, sorry, delete that, 98.9 megahertz, and we're already reading a deviation here, but you can then change the IF bandwidth. At the moment we've got it 280 kilohertz, so if it's distorted, then we can adjust it. We've got a squelch control and a volume, so if I minimise the squelch, and then we've got a signal there coming in, so it'll give us the dBm level, the deviation that we're currently receiving as well. It'll show that there too. So we've got all kinds of little options. We've got an oscilloscope, obviously, so we can look at the mod further and the speech that's currently being broadcast on that radio channel. So it's a nice little off-air receiver as well. It's quite useful. Obviously it goes the full range of the instrument, but it's pretty decent receiver, pretty good to have. Another thing as well is we can select the spectrum analyzer from the bar charts we were looking at earlier with the off-air receiver, and we can go to spectrum analyzer, and then we can see as much radio spectrum as we want to see that's coming in off the antenna, and naturally that's something that the wire antenna is picking up, so that's quite useful as well. And then we can expand on that if we want to, and then naturally look at the radio spectrum in greater detail as well for off-air. Okay, so that's the end of the review video. You can't say that it wasn't detailed. Showed as much as we could of the instrument. Definitely worth the investment if you get the opportunity to purchase one of these test sets. Very, very well made, very fully featured. Great little test instrument for the bench and for professional use as well as hobby use, etc. And very well made indeed by Marconi IFR Aeroflex. Hope you've enjoyed the video, and please stay tuned for further videos, and look forward to seeing you in the next one. Thank you for joining me. Bye bye now.